Okay, men, welcome to our first day of notes. We're going to go on to section 10.3 of paired data. So right now I'm just looking at the definition of paired data. Paired data result from recording two values of the same quantitative variable for each individual or for each pair of similar individuals. To analyze paired data, you're going to start by computing the difference for each pair. Then you'll use the mean difference and the standard deviation of differences for our summary statistics. And when you have to make a graph, you'll make a graph of the differences of these values. So when we take a look at the normality check, we're going to make a normal probability plot of these differences. So I started off talking about Mr. Downs here, and Mr. Downs writing a chemistry test for students in the school district. So Mr. Downs used a matched pairs design to collect data on scores for two different versions of his final exam for 20 students. I'm asking you to construct and interpret a 99% confidence interval for the true mean difference, version A minus version B, and final exam scores for chemistry students in this district. So I already went up and wrote this out to save us some time. So remember, when we're talking about panic, because we're constructing a confidence interval, we're going to follow panic, parameters of interest, check my assumptions, name the interval that I'm going to construct, actually calculate the interval, and then conclude in context. So I'm going to say mu sub A is the true mean final exam chemistry scores for version A in the district. Mu sub B is the true mean final exam chemistry scores for version B in the district. And so I'm going to take a look at mu sub D. And mu sub D is the true mean difference in final exam chemistry scores in the district, and that is version A minus version B. Checking my assumptions, I see that I did take a simple random sample of 20 students in the school district. That's stated in the prompt. For my normality check, again, as I stated previously, I'm going to make a normal probability plot of their differences. And here is that normal probability plot. I know it's awfully small, but it appears to be roughly linear. So therefore, the sample distribution of the difference in sample means is approximately normal. Looking at my independence check, again, we saw some examples previously this week where we did not need to check independence, and that's because we were looking at volunteers. We selected these students randomly, so therefore it is important for us to check. And we see that, yeah, we have, safe to assume that there are probably more than 200 chemistry students in a large district. So I say that the independence check has been satisfied. Okay, so the name of this interval is a one sample t interval. It's one sample t because we have paired data. So we're going to look at a one sample t interval for the true mean difference. So when I calculated it, we got a 3.2 for the average difference, and my standard deviation was 3.533. Since I had 19 degrees of freedom, for a 99% confidence interval, I have that at the top. My value, my t table says that is 2.861. So 3.2 is the point estimate, so that's x bar plus or minus 2.861 times 3.533 divided by the square root of 20. I get 3.2 plus or minus 2.260, and I get an interval of 0.94 to 5.46. So then here's our favorite phrase. We are 99% confident that the interval from 0.94 to 5.46 captures the true mean difference, version A minus version B, in final exam scores for chemistry in this district. Again, I'm concluding about the students in this district. Our next example that we're going to take a look at is what do we do when we have a significance test? So rather than have to do all these checks and conditions, I'm going to use the previous example of Mr. Downs, where he used a matched pairs design to collect data on scores for two different versions of his final exam for 20 students. So recall that we had the sample difference equal to 3.2, the standard deviation was 3.533. The question is, do the data provide convincing evidence at the 1% significance level that there is a difference in the average test scores between version A and version B of the final exam for chemistry students in this district? Well, we've already defined the parameters of interest. So to save everybody time, I just copied and pasted the parameters that I defined in the previous example. So we've already gone through it. Here's where we have to define the null and alternative hypotheses. And because we are looking in the previous example, 1% and comparing it to a confidence interval, also it says that is a difference. So we're going to say that there is no difference or that there is a difference, and that's going to be not equals to for the alternative. Again, I'm testing at 1% level. Good news for you is that we've already done all the assumptions, so the assumptions stay the same. So everything is good here. So all of our assumptions are good. So now I'm going to take a look at the name of this, and it's a paired t-test. You could also call it a one-sample t-test for a mean difference, but I like to call it a paired t-test because we're looking at the difference of our paired data. So here's our formula for t. We're going to take a look. T is equal to, because we don't know the population standard deviation, so t is equal to our x-bar difference, our sample mean difference, minus 0. We're going to take this our standard deviation of our sample and divide it by the square root of 20, because that's the number in our sample. So when we do that, we get a t-score that's 4.05. So I'm going to draw my t distribution. I got negative 4.05 and 4.05 because it's two-sided. We had 20 people in our sample, so 20 minus 1 gives me 19 degrees of freedom. So I'm calculating the probability that t is greater than 4.05 using the t-CDF feature, and I get 0.00034. Since it's two-sided, I have to multiply it by 2, so that gives me my p-value. My p-value is 0.00068. Okay, since p is less than alpha, we will reject the null. I did not write in here comparing it, so I would, since p is less than alpha, and we're going to say that 0.00068 is less than 0.01. So now, summarize in context, we have convincing evidence that there is a difference in the mean test scores between version A and version B of the final exam scores for chemistry students in the district. This is consistent to the confidence interval that I constructed in the first example. Okay, so in section 10.2, we used two sample t procedures, and in 10.3, we use pair t procedures. So you're going to have to decide on the AP exam whether or not I'm going to use a paired t or a two sample t. And, you know, the proper inference method depends on how the data were produced. So let's take a look at this example. It says some students in a very large district wondered if students who took AP statistics in high school have greater IQ scores on average than students who don't take AP statistics. To investigate, they took a random sample of 10 AP statistics high school students in the district and a separate random sample of 10 non-AP statistics high school students in the district, and had each of the students take an IQ test. And here are the results. Do the data provide convincing evidence that high school students in this district who take AP statistics have a greater mean score than high school students in this district who don't? So the answer to the question, is this going to be a paired t or is this a two sample? I look and I have two different populations. I have those students who took AP statistics that I sampled from, and then I have non-AP statistics students that I sampled from. So just thinking ahead, this is going to be a two sample t test because they're asking me, does it provide convincing evidence? So Parameter of interest, I'm going to let mu sub AP equal the true mean IQ score for all high school students in this district who take AP statistics. I'm going to let mu sub n equal the true mean IQ score for all high school students in this district who do not take AP statistics. And then I'm going to define mu sub d, the difference, as the AP students' IQ score minus the non-AP. So I get to the null hypothesis that the difference is 0. The alternative was in the question is that they believe that the AP students have a higher IQ score than non, so they say that the mean difference is going to be greater than 0. No significance level was given, so I'm going to test at the 5% value. Taking a look over here, it says that my students, AP and non-AP students, were taken randomly or selected randomly. So I'm going to take a look at both normal probability plots for the AP students and the non-AP students. And when I take a look at both of them, I see that both the normal probability plots are roughly linear, so therefore the sampling distribution of the sample means is approximately normal. You know, I keep saying the normal probability plot. If you guys wanted to make a dot plot, or if you guys wanted to make a box and whisker plot, you could also compare them. And if you did, you need to take a look for skewness in their graphs because these values are small. I just like the normal probability plot, seeing roughly linear, therefore it's going to be approximately normal. I need to take a look at the independence because we selected these people randomly. And it's safe to assume there are more than 100 AP Stat students and 100 non-AP Stat students in this district. So as I mentioned previously, this is a 2-sample t-test for the difference of means. So my t-score is going to be the sample means, the difference in those, minus the parameter, which we thought is 0, not parameter, but pardon me, the null hypothesis of 0. There is no difference. This is the standard deviation of the sample for AP, and this is for non-AP. Carrying it out, we get 7.8 divided by 2.17. I get a t-score of 3.59. I'm going to use the conservative method. If you run a 2-sample t, please write down what that degrees of freedom is when you run the 2-sample t. But I'm going to use the conservative approach. I got 9 degrees of freedom. I look at my means. They're both 10, so 10 minus 1 is 9. So I draw my t distribution. Here's my value of 3.59. I'm looking for the area to the right. So I'm going to use the TCDF feature, and I get that it is 0.003. So since p is less than alpha, 0.003 is less than 0.01, we will reject the null. There is convincing evidence that high school students in this district who take AP statistics have a greater mean IQ score than high school students in this district who do not take AP statistics. I hope that you guys found this to be pretty beneficial. One thing that you might want to get used to is talking about what that p-value means in context. I had that on a couple of questions, so I'm just going to summarize that here for you. What does this p-value mean? So assuming that the null is true, there is a 0.003 probability of getting a difference in AP statistics students minus students not taking AP statistics in mean IQ scores from the samples of 7.8 or greater just by the chance alone. I thank you guys for taking the notes. I hope all is well, and if you have any questions, please do not hesitate to ask them on our discussion thread. I'll put the homework assignment on Schoology for you later. Take care, men. Have a great weekend.